So I'm Ajay Wasan from IIT Roorkee. I'm also setting up a lab. So I'm just on a baby step. We are shifting from the mod to this single atom things. So what we initially are working in the quantum optics. So I will discuss how everything has shifted from quantum optics to the quantum computing. What is the connection is there? And in fact, when I joined IIT Roorkee, so suddenly I found a lot of papers started coming in quantum computing. I knew in those PhD days, those were working in the quantum optics, now they are doing quantum computing. First thing was that India at the time it did not start. First thing was that how to find out where the connection is there. So even there were no books, so somehow on the net, some friends. So whatever I will try to show here. So generally we know if there is a atom, light falls on it, atom absorbs the light, emits the light due to this spontaneous emission. And if light is passing from suppose I have this glass cell, these rubidium atoms are there. So I have passing on light, so I have two options. Either I can collect this light on the detector, or scattered light I'm taking on the detector. If I'm seeing this detector, so I will be finding the transmission here. Obviously, when at resonance frequency, transmission will be less. And if I'm collecting the scattered light, then at resonance, light will be more there. It will scattered more light. So these are simple things we already know. We read all these things in our bachelor and graduate. And we are taking just simple two-level atomic system. And here we're considering classical plane wave. And we are taking this quantum mechanical, this two-level atom. There are many levels in the atom, but we are taking only where this light is interacting with the atom. And we are also applying this electric dipole approximation. Atom size is very small compared to the wavelength of the light, whatever I'm using here. So one more terms comes here, we call it Rabi frequency. Basically, it depends upon the dipole movement between these two levels, and electric field, whatever light, divided by h bar. So this shows what is the coupling strength between the light and the atom. So this omega will come few more times later on. And one more thing, when we are solving it, Hamiltonian for this, so we have a bare atom, Hamiltonian, interaction Hamiltonian, and when we solve this in the interaction picture, so you will get this Hamiltonian. And I will use this Hamiltonian to show how it is converting in the single qubit gates. I will be using this one. And this will you find in Metcalfe book, and many books are now there. And if you solve it, you are going to get the energy as in values. And it shows that when light field is on, the level will be shifted. We call this also AC Stark shift. And you can also find in the book, they use the word pressing of the atoms. Many names coming here. But my focus will be in the coming slide, will be here. Okay, I'm now coming to the Rydberg atoms, because if we have to do quantum computing, we have to use the Rydberg atoms, because when atoms in the Rydberg state, then it's strong dipole moment, and dipole interact, that properties we have to use. So here I'm showing this upper levels, we call it Rydberg state. Mostly above 20, all the levels we call Rydberg state as per the literature, but we'll be using around 70 in the whatever published paper in last 10-15 years. They are using above 70. And here basically atoms are very far away, so quantum number is very high, the radius is also very high. So we can also represent like this, same thing. This is the Rydberg atom is far away from the center. And for the hadronite atoms, we can write this energy here 13.6 over n square eV. You must have seen with the hydrogen, but here we are using n minus delta L because some quantum defects come here. And this is important only first, second, third, initially few terms, not later on. And other important properties of the Rydberg atom, you can find out on this thing. That is the lifetime. As n increase, atom lifetime increase. Other thing, resonant dipole interaction coefficient, that is proportional to n power 4. When as increase, I said this will also increase. And van der Waals interaction coefficient, that is n to power 11. That's a huge number. So basically, we will be using, and this we use these two terms in tau. So I just give the idea in Bohr models when we are taking this radius when you far away from the center, the Rydberg states that this is almost proportional to n square a naught. And if nq I'm taking the n value I'm taking 60, so this lifetime in this case is going to be 100 microsecond. Just compare when we have atom, let us say in the sodium, it's in a nanosecond, S and P, when we take the ground state and the upper first P state, that is nanosecond around some 20 to 30 nanosecond. But now that has become a now 100 microsecond. That is more than enough to perform this quantum computing type of experiments. And other thing important, it has a very large dipole element. So I'm taking, for example, these to some state you can take anyone. So NL, or this is N changing, or L is changing by plus minus 1 because electric dipole allowed transition something. So in that case, that is also N square E naught. So it's a large dipole interaction. So generally, as I said, this is a Rydberg state. And if you want to go from here to here, we have to use the ultraviolet light. Unfortunately, it's a very expensive. If we take this, let us say we want to make 200 or 300 nanometer light, it's very expensive. So alternative way is we use 2 laser pulses. So here I'm showing is 780, and or you can use 480. So this Wisconsin group, Professor Sefman group, they are doing this. They are using this one, 780 and 480, and one they are going to the 1790, and one other group, Harvard University Lukin group, they are using 420 and 1013, and they are going to the 70s. And in fact, this combination has given the better results so far, whatever published till date. Because in this case, fidelity is higher compared to this. Okay. So what is a qubit? I'm just showing a qubits. So I'm just scaling it downside. Same picture, but here I'm showing upper levels are qubits and ground GG. This is a Rydberg states. So we have one option. We can make a GR qubit, ground state, and Rydberg state, that qubit from 0 to 1. So in that case, we have to use the 2 light source, laser beam, or I can make a this RR qubit. In the upper state, I can take qubit like this. And other option, whatever most of the labs are using right now, in the ground state, I can take 0 and 1. But this is not a electric dipole allowed transition. So I have to use one more virtual level. This is very far away from this transition. Because if I bring this, if I have to excite the atom through this, then a spontaneous emission will take place. I have to avoid that thing. So now there are tricks. Yeah, we said adiabatically removing this level. So all this mathematics and everything available. So we can go with 100% efficiency from here to here or here to here. So you know in the beginning where is your atom? You are here or you are here. So separation between this around some 1500 terahertz. This separation, Rydberg state, Rydberg qubit, I'm talking that it 10 to 60 gigahertz. And within this, I'm talking about only the rubidium and cesium atoms. And if you are here in the ground, that is from 0.5 to 10 gigahertz, this separation. So initially, I showed you one Hamiltonian that was written in the matrix form. Same thing I'm writing in the basis. This A and B, I'm taking the ground state, this state. I'm writing this basis form, and I am writing at some local, suppose I have some trapped atom. At that certain atom, what will be the detuning? Okay. And there will be some phase, some is also coming. Here I'm taking h bar equal to 1 because we have to divide by h, so I have removed. And this is some local phase will be also there. That is the same Hamiltonian that I showed in the beginning. And if I take a simple case, let us say I'm saying this is the omega and this is delta. And for a fixed gate time, I'm applying one pulse. So this omega I'm giving for a certain time. So I know what will be the pi value, what will be 2 pi value. We know already. We have to do all this thing. So I'm doing for this tau g. And if I calculate the unitary matrix, how the time evolution is going on of this. If I put here exponential this thing, this is also a standard thing. If I substitute here and if I solve here, I will end up here. And this is very well-known equation. If you use, I will show you soon. So here, whatever omega tilde is here, basically omega square delta square. D, you can also do this thing, and X, Y, Z. So anybody interested, whenever free, you can ask me. I have calculations are with me. Now, this equation is given in the Nason-Chuang, chapter 4. When rotation gates are coming, single qubit gates are coming. So I'm taking simple case, taking delta is equal to 0, it means at resonance. And this value comes coming this. And if I put phi is equal to 0, I'm getting the rotation Rx gate, Rx theta, Ry, Rz theta. So whatever I want to do, this is in the Nason-Chuang, you'll open, you will find all these gates, 3 gates. So you have 2 levels, you have to give the right frequency, and automatically in the nature is giving us, we are getting all this Rx, Y, Ry theta, Rz theta. 3 gates are coming. Either you take a 2 qubits, or you take this allowed this electric dipole I showed you, diabatically we are rooming. Even you can do there, same thing comes there. So whenever you are applying the right pulses, automatically one gate is there. And which gate you want, it depends upon what you want to do. Okay. So I was talking about also this. So previous case was simple case. Even suppose I solve this thing. When I came here last time, here in the same place, I showed what is the calculation of this. So I'm just going, even if you, I think some recorded talk is there, you can find out there. Even you solve this thing for a proper frequency and all this thing. So we end up with this unitary matrix. And you see again, whatever I showed in the previous slide, again same matrix is coming here. This is also rotation gate. So this is one global phase. This is some single qubit phase gate, and plus rotation about, actually in the previous slide I was using this omega t is equal to theta, the same thing basically. So we have again some rotation gate is there. So depending upon which, suppose we are doing single qubit gate, so even we can do everything from here by these 3 rotation gates. Okay. Now I come to the Rydberg atoms for multiple qubit manipulation. So I will also show here whatever we are getting here 2 by 2 matrix, similar type of matrix will come also here. So I'm just taking 2 atoms and they have to be nearby, but outer atom should be pretty far from the center. I mean in the Rydberg state. So this interaction term, dipole-dipole interaction term, you must have seen already in your books. Electrodynamics by Griffith. Here this DJ is I'm taking jth atom, this kth atom, the dipole operator here, this is dipole operator here, and n basically showing from this to this direction. I'm showing arrow here, and R is the separation. Okay. If I'm taking energy levels of this atom and this energy level of this atom, I'm focusing first here. I'm taking to in the Rydberg state. I'm taking to this Rydberg state. I'm calling this A. I'm calling this B. This is C and D. And then I'm saying this dipole moment is here DAC, and this dipole moment is DBD. If we solve this Hamiltonian, it comes this. Only thing is that in the previous case, that there was single qubit. Now we are getting here tensor product of AB and tensor product CD. These are the states in this case. And we are neglecting the, in this calculation, when we solve it, so generally one angular part comes here and neglecting, we are just taking 2 parallel dipoles, or that is a simple case. So, but thing is that when we are taking this eigenstate, combined eigenstate, so basically they don't shift. And this shift, we call it Postert effect. So when we are doing more correction, so Hamiltonian come in this form. Okay, and here Postert effect basically you can see here we are taking EC plus ED, energy of this, and minus EA plus EB. So these two are subtracting. If they are equal, so we are getting this result. Otherwise, some small frequency difference will be there. That also matter. I will discuss. So here 2 cases come. One is when we saying this Postert effect basically at resonance basically is equal to 0. In this case, what happened? If there are 2 Rabi levels are there, let us say in the same species, then the same species. So this separation will be equal, this separation will be equal. If I'm exciting one, the other will come here. So we call this resonant interaction, delta F equal to 0. So whatever I showed in the previous equation here. So we are writing in this form, like this. So our Hamiltonian will be, so this term is coming there, then this combined states AB and CD, and that's Hamiltonian. The B can write in simple way, this AB, CD, because here this thing and this thing, because A there, B is here, because you see from here, this interaction basically take place between this. I'm just see here, we are bringing this to this. In fact, when we solve this Hamiltonian, automatically when eigen energies and eigen values comes, and when you get the eigen function, automatically this comes together. Okay, so same thing I am showing here. This is Hamiltonian, we are adding simplified as A, B, C, D, J, K, but this is between the upper two Rydberg, that interaction is taking place. Or as I said, we are taking the same species, so this A and D, they are NS, and B and C, this is NP. And other case, when this delta is very large, greater than this value, then we call it van der Waals. And in fact, you can make out, when I was showing this Hamiltonian here, just this Hamiltonian, this is the off diagonal terms. These are diagonal terms. So this is the diagonal. So I'm showing the CD, this term, and these are off diagonal terms. Just like in the two level atom, same thing coming here. Okay. So in this case, now we are saying this is very, very greater than this. So we have dropped this, only this one is there. And this C6 components here, basically we are defining here by this. If we are taking the square, then it becomes C6, otherwise this is C3. If I will call this thing C3, so only this term. Okay, and we are again taking the same Rydberg state, but people have done the calculation for different species also. They are bringing the rubidium, cesium, they are doing all this thing. Hold the two atom and different species and bring near them, you will find little different term value will come, depend upon the dipole. And this is, it can be attractive or repulsive, depend upon the detuning.
Jay, what about the C8 coefficient contributions?
C8. But
that can also contribute.
But I'm not going up to that far, John, far away. But it may come.
But like this is the second order effect.
Second, you can get the same thing by second order perturbation theory.
What about the quadruple moment contributions?
But so far I have not seen whatever papers I have seen. People are doing calculation. That way I will not say people are doing.
P states you will not have quadruple moment, but for P states you may get, right?
Upper one.
Yeah.
But so far, whatever, let us say, Safman and the Walker-Safman, they have published the review of modern physics. Maybe you have to check how much effect come there.
That's R8, in the denominator you will have R8. Maybe after R8. Maybe that.
So how much difference comes? Frequency that we have to send in megahertz, you have to see. Suppose megahertz and kilohertz, then contribution will be very less. So whatever I'm just saying, whatever I showed in all previous slide, you can find out on the Brove's lecture. Here on the nets they are available. But he has told in very simple way. He has taken some toy model. But whatever I'm showing there, previous calculation, they have been done through proper perturbation theory and all these things. So basically this is a Hamiltonian. And we are taking two conditions. If either this is less or greater. When this is less compared to delta, then we are saying this is van der Waals. And when this is greater, then we are saying this is resonant. Delta is equal to 0, that condition. So we are getting energy here in this form, we are energy getting in this form. Okay, so what we learned here, suppose I'm taking two atoms from ground to Rydberg, I can excite Rydberg state. But if I'm taking two atom interaction, I'm taking to bring together. So what happened? From GG, it can go to GR, it can go RG. But I cannot excite both the atom in the same time in the RR state, Rydberg state, because due to this van der Waals, this energy shift take place. One of the atoms level will either shift either up or down. So I will show in the coming slide. So basically, just remember that I can excite. Suppose I am from this position, I can excite the atom here. But when I am in this position, I cannot excite both the atom together in the Rydberg state. This thing we learn here. Okay. So it's written here when H delta mu is very less than U van der Waals, no excitation of Rydberg state. We call it blockade terms comes there. So in the laboratory, we have to hold two atoms very near. One atom in one, we are making this optical fusing array. We have to hold one atom here. And other thing important, you can find out the statement paper. Yeah, I'm showing I'm this region given dipole interaction we're taking. So this is the resonant case and this is the non-resonant case. So when we go from here to here, so if you go on the scale, when interaction take place, this is almost 12 order of magnitude compared to when they are in the ground state interaction is taking place. So advantage is in the atoms, we can excite the interaction. For example, ion trapping is there, so they are charged particle, always Coulomb force is there. But in the neutral atom, depending on the requirement, we can excite the atom and then interaction will come. If you don't want, it automatically will go after some time. So depend upon requirement, we can make it on off. You want interaction or you don't want interaction. So this blockade thing I was showing, suppose I excite one atom here, and if I try to excite my other atom, but this atom will not excite because this energy level will shift, as I said there. So this shifting will depend either this side or this side, depend upon the detuning. Which detuning happens with respect to this. So we know already the C0 gate, we donate by like this, and here is the control qubit. Here this is a target qubit. And when we are applying here, so we know this, if we are applying 0, 0, this will be 0, 0, this is 0, 1, this is 0, 1, this is 1, 0, then become 1, 1. And when this is 1, 1, this become 1, 0. Because whenever this is 1, it will turn on this, turn off, 0 become 1, 1 become 0. And just now I was talking about this UXY rotation gate. So now suppose I have this rotation gate, UXY, whatever I was discussing. So here this, it can be GR or GG qubit. One ground, one upper, or one G ground this qubit we are taking. So in this case, then whenever this depend our choice, we want to operate when it is 0 or when it is 1. It depends upon choice. So for example, I am taking here, sorry, I went back here. I am taking this thing if I want to write in matrix form. Okay. I want to write this thing in matrix form. So I have to write like this. So right now I'm just writing when I want to turn on the UXV, I am turning on when this is 0, 0. Or if I want to turn it on when this is 1, 1, then I have to keep, actually I made a mistake, this should be I. This should be I. And if I'm solving this, I will end up with this matrix. Now, I'm taking this same thing can be obtained, whatever I have shown the gates just now, unity matrix. I'm taking G0 and then Rydberg state, I'm taking 1. And if I write this unity matrix in this form, I'm writing here HCT. It means I'm taking two Rydberg atoms. I'm exciting both of them in one shot. And Then I'm again applying the one pulse to the target. And if I solve this unitary matrix, I will get this. And to solve it, it's just a simple, as you know, simple rule, e to the power ix you have to take here Hamiltonian and then apply, expand it, lot of terms will come. Then apply simple mathematics, we can get it. But problem becomes, so many multiplication comes. If you do by hand, it will take 4 or 5 pages, A4 size pages. If you do with the Mathematica, just a 5-minute job, you will get all the terms. You have to only collect all the terms and find out which one you have to neglect, which one you want to keep. And if you want to be more faster, take Python. They have a symbolic quantum mechanics. Result will be in 2 minutes. What is the result of this? Whatever I am showing here. So you can do this thing using the Python. Okay. So now we are doing, initially I had a mod. Recently we have got this our new system. And we will be making the 2D mod here. And we got it. Now we are preparing for pushing from here to here. And here we are making 3D mod. And this 3D mod will be transferred to the optical array. We are making an optical tweezers array. They will hold the atom, but that is, my one student has done a lot of calculation, how to remove the extra atom from the each optical tweezer. That we are doing. In between, we are also preparing Raman layer. As I said, I'm taking my qubit, this one 01, so I have to take the atom from here to here or here to here. So we have a layer. We are waiting for the CVG. And we are waiting also for a scanning every parad thing. And I don't have money to buy this arbitrary wave function generator right now. Let us see how it goes. But we need it. If we have to, we make sure, because before starting the experiment, you have to be 100% sure whether you are at 0 or you are at 1. Otherwise, all the atoms you have to be in, you have to give the pulses from the outside, make 100% fidelity here or here. And this is a chip rack grating. Looks only one grating, but it's costing me around 6 lakh rupees right now on the weight. So we will be doing something like this. I brought all this from the Lucan group paper. We are also doing similar thing. I have a AOD has not reached, but I have a driver now right now. So I cannot do anything. So we have to make multiple beam here within this vacuum cell. For the first I have to make the mod and multiple beam. And then atom trapping is showing here for each beam trap, atom trap. Similar thing we will be doing also. And then advantage here with the AOD and applying frequency from outside, we can change the separation between the two atoms. And we can see the interaction, which one is the best for me, because matter on the geometry. And this is a FN group. So they are using, also here you can see they are using this AOM here. So one AOM you are using, so you will get the beam in the horizontal level. If you use one more 2 AOM, so you will get the 2D structure. And it looks very simple, but it's not that much simple as looking on the picture. And the people have already making the arrays. We are also hoping the same in the coming days, because a lot of groundwork has been done. Many things I have right now. That maybe, hopefully, when I will come next time here, we will show you some result like this. Thank you.
Hello, sir. So You talked about the connectivity of qubits, right? Like in the AND trap setup, the qubits are connected by the Coulomb interaction. So how are the qubits connected in neutral atom?
No,
Can you explain?
Here, see, you have atom. You put the atom in the out, far away from the center. It's like say dipole. It will just like a dipole. Now you bring one dipole and second dipole. Their interaction will be more compared to the two neutral atoms. You must have read dipole in your class 12. Same thing you think in that way. One plus charge, one minus charge.
Okay. So I have heard that the connectivity in the neutral atom is better than the other systems.
No, you cannot say. See, many approaches are going on. Here, of course, just think in that. First, you try to. I have a plus charge here, minus charge here. Okay, you see my one dipole.
Yeah.
I can make also. Then we bring one term I showed you, the interaction term I showed you, d1 dot d2 minus 3 d1 and d2 and divided by RQ, something I showed. That is the interaction term. If you compare, if you take a two atom, sorry. No, it will be not in the camera maybe. If you have a two atom, it's a neutral, even bring very less interaction is there. One place I showed, when you have a dipole, then 10 to the power 12 magnitude higher than this interaction.
Okay.
And that interaction, what it doesn't allow to come the atom, it will not allow other atom to come to Rydberg state. That thing we are using for entanglement.
Okay.
What's the point?
Any other question? Your setup, the ion pump, is there 2D mode side or in 3D mode side?
3D mode side.
So 2D mode side, you don't have any ion pump?
No.
So how do you maintain the, I mean, it's not required, the 3D side?
See what they did, they have put the two tungsten source here. Ion pump is here, 2 liter ion pump. And we have to turn on for some time, but it is some small hole is there, micron size hole, taking full care. They are saying you don't have to worry.
Okay.
Lifetime is around 5 years.
And what is the size of this differential pumping tube?
This one?
Differential pumping tube.
We have that is point micron size I said.
Okay.
So Ajay, at this stage now 2D mode is prepared, right, in your lab?
We are seeing the student, we are seeing the mode, but still we are trying to stabilize. We have to make it a little longer.
So is there a way to measure purity, state purity?
State. See, that we have to do here, state preparation, but once we have to make the laser ready, you have to see only the fluorescence. See, once I was saying, suppose you have atom here, you have connect with the upper line. You have a laser. If you suppose you have put from here to here, and if you put here, no spontaneous emission
So
will
that
come.
contrast will give you.
So you have to check from there. And these people, Lucan group, they do just once, and they don't check it. And from the result, they found out where the atom was there.
And how much purity they get?
They are getting 99 point.
Okay.
Plus they are getting, but they are using this, I said 420-11-1013. And even last time in your this, IISER Pune, when Russian group came, so they had some calculation, they were telling all this thing.
Any other question? Okay, if not, let's thank Professor Ajay Wasan again.